Today, we're going to start on chapter 15. And in chapter 15, we finally get to address something that we've put off for a long time to address, namely what the nature of benzene is and other molecules that are in the same class that we call aromatic. We'll learn that there are other species besides benzene that are aromatic. We'll learn what the nature of aromaticity is as far as we can. One thing I do want to warn you guys about, maybe warn is a little too strong, inform you guys of going in, is that aromaticity is not a uniquely defined concept. That's something I got trained to say a long, long time ago because a goodly chunk of my PhD thesis had to do with aromatic compounds. And when I say it's not a uniquely defined concept, by that I mean that it's not something like pH, where you can stick in a probe and it comes back 7.9. You know, pH is a uniquely defined concept. pKa is a uniquely defined concept. Aromaticity is not. It's rather a loose conglomeration of properties of molecules that are like unto benzene in one way or another. But by the end of today, we'll have gone over Huckel's rules, which do a pretty good job at helping us to predict whether a molecule is aromatic or not. And we're going to have to wait through Wednesday to go over that fully. That's going to be mostly what we talk about on Wednesday, which is, here's a molecule I've never seen before. How can I tell whether it's aromatic or not? And we'll cover that on Wednesday. For today, and of course I've drawn benzene over here. We've been drawing benzene for quite a long time at this point. And I think by now you're aware that benzene exists as a resonance hybrid of the two so-called Kekulé structures, named after the guy who first figured out the structure of benzene, or it came to him. The sort of folktale version of it, I don't know to what extent this is true, is that he fell asleep on a bus one day and it came to him in a dream while he was asleep on that bus that he realized benzene was a ring like this. But remember, of course, when we draw resonance structures, remember this is not an equilibrium. And those of you who know me know I'm saying that for my benefit as well as yours. It's not an equilibrium. There's no flipping back and forth here. I don't know. I guess if something like that came to you in your sleep, you'd be famous, so that's not so bad. In any case, so right, it's not flipping back and forth. Benzene has one true structure, but we can't really show it using this standard valence bond, what's that? This standard valence bond model of structure drawing. So people try nonetheless, and you'll sometimes, actually fairly often, see benzene drawn like this with a circle in it. Let me make that a little bigger, which I'm completely fine with that, by the way. Actually, I often, if we were using chalk on a chalkboard, I usually draw benzene something like that. But it depends on what you're trying to communicate. You know, there's times when, in fact, coming up pretty soon in chapter 16, there's times where we'll be doing mechanisms with benzene and related compounds. And then we really have to put in bonds, put in pi bonds like this. But we need to remember that benzene exists as a resonance hybrid, and there are not actually localized pi bonds like this. So benzene is not an alkene, and benzene doesn't behave anything like alkenes. We do know something about how alkenes behave. We learned about that in chapters 7 and 8 mainly. A little bit in chapter 6 too, I suppose, where we learned that alkenes undergo addition reactions with a whole slate of electrophiles. That was chapter 8. That was your first exposure to a whole bunch of reactions all at the same time, but they all had that in common. They were all addition reactions of alkenes. Aromatic compounds do not undergo additions with aromatic compounds. Rather, I'm sorry, with electrophiles. Aromatic compounds do not undergo electrophilic addition. They can react with electrophiles, but as we'll learn in chapter 16, you got to kick them a lot harder. And even then, they don't undergo addition. They undergo substitution reactions. So that's chapter 16. We'll get to that. Good. So I think that's all I need to say about it. I want to say a little bit more about the structure of benzene, but it was not intuitively obvious for quite some time what the structure of benzene was. And I mentioned in the class notes some interesting wrong guesses that people had at first about the structure of benzene. So, but at first people knew that its empirical formula, not molecular formula, but empirical formula was CH. In other words, there were equal percentages of carbon and hydrogen. On a per atom basis, it was 50% carbon, 50% hydrogen. So they knew that. Later on, they determined its molecular formula was C6H6, which we all know now. That was still not enough for them to get the structure right. I'll show you a couple of things that they thought it might be. That compound also is C6H6. And as you can imagine, stupidly strained. Both of those compounds are known. They've both been prepared, and neither of them is at all like benzene. This compound here behaves like any other alkene, only more so because it's so strained. And actually, for what it's worth, I thought of another one. Well, it's not like I invented this compound, nor that I'm the first to notice that this one also has C6H6 as its formula. Why don't we call that guy 2,4-hexadiene? Sounds good to me. As to what these guys are called, I think they call this one prismine or something like that. It's kind of like a prism. I don't even know what they call that one. But you know what? I'm pretty sure that, and I'm only bringing this up because, again, people always ask me, what's that called? And I don't always know. I mean, it would be, without the double bonds, it'd be, let's see, bicyclo 2,2,0-hexane. But with the double bonds, I really don't know what they would call it. Let's see. There is like a single mouse click, name the compound thing. Check structure. Convert structure to name. There you go. That's what that's called. So not that I really care if you know that. So all of these have been prepared. All of these are thoroughly well-studied compounds. Not one of them is anything like benzene. So none of them behaves like benzene. But they eventually did figure out this structure. Like I said, Kekulé came up with that. And that's why we call these two structures Kekulé structures. But that still leaves for us to discover, since benzene is not an alkene, what is it and how does it behave? And that's really the subject of chapters 15 and 16. Now, a couple other things about the structure of benzene that you guys should know, probably do already know. There we go. First of all of the carbon-carbon bond lengths in benzene are equal in length. So that's further proof. This is known. It's been the crystal structure of benzene has been long since calculated and studied, and so we know all 6 of those carbon-carbon bond lengths are the same. All 6 of the carbon-hydrogen bond lengths also are the same. But in terms of the carbon-carbon bond lengths, Normally, we would expect double bonds to be shorter than single bonds, right? So that shows us that these aren't really double bonds. There's something in between. And in fact, if you want to think of benzene as having 6 equal 1.5 bonds between the carbons, I'm okay with that. That is not wrong. That's a perfectly valid way to think about benzene. Also, all of these bond angles are exactly 120 degrees, which again would not happen if the double bonds were localized rather than delocalized. And all that's going to have to do with the stability and the structure of benzene. So if you have just a standard carbon-carbon double bond, I won't even specify what those other 4 bonds are going to, because it doesn't really matter. We know that you can treat this with all kinds of different, with that delocalized, easier to form benzene than really do anything to it. Something like that will gain some insight into the energy of formation of benzene from its reactivity. And I'm sort of peeking a little bit ahead to chapter 16. But in chapter 8, we saw all kinds of reactions where you treated alkenes with electrophiles of basically this type. And we saw that these things underwent, actually, I'd kind of prefer, sorry to be thinking on my feet, but I'd sort of prefer, if I may, to show it like that. The alkene plus the electrophile XY will give us an addition product. So again, that's chapter 8. If you've forgotten any or all of those reactions, now would be as good a time as any to review them. I'm not going to reteach them, though I did put my class notes from last term on eCampus, so you can look them up if you have need. But we will get an addition product of this type. Benzene doesn't do that. It will react with many of those same electrophiles, but only under much harsher conditions. So for example, and a lot of them it won't react with. So for instance, if you treated benzene with, let's say, HBr, which we understand would be one of these XY type electrophiles, right? If you treat an alkene with HBr, you'll very quickly get this alkyl bromide. You would expect to get the Markovnikov product, and so on. But if you treat benzene with HBr, no reaction. They just look at each other. If you were to treat benzene with ozone, let's really go crazy. Ozone is just stupidly reactive. It's one of the strongest oxidizing agents that there is. No reaction. Alkenes will certainly react with ozone very quickly. And after a reductive workup, remember that's the one where we cut the double bond with our scissors, and then we stick oxygens on with our oxygen tweezers. Or if you had Dr. Pennington, he's much more violent than I am. He told you that you cut the double bond with an axe and then cap the 2 bloody stumps with oxygens. Whichever works for you, but benzene does not react with ozone, not as far as I know. You can go even further than that. Potassium permanganate. The permanganate ion also is another one of the strongest oxidizing agents known to man. That will chew up alkenes in a hurry. No reaction. And chemists found this out pretty quickly before they fully understood the structure of benzene, and they were just astonished at its lack of reactivity. You treat benzene with bromine, no reaction. Unless you add a transition metal catalyst, I'm sorry, not well, it could, yeah, it doesn't have to, it could be a transition metal, but a metal halide catalyst, such as aluminum bromide or iron-3 bromide. And we'll learn about this reaction in chapter 16. So you don't have to know about this yet, but we'll get there in chapter 16. And even then, by the way, I can hardly express how nasty aluminum bromide is. It's fuming and horrible stuff. But even then, you don't get an addition reaction, you get a substitution reaction. And the product in this case will be bromobenzene, as we'll cover in chapter 16. So HBr is also a byproduct. So something really strange is going on with benzene. And as I said, they figured it out before they understood the structure of benzene totally. To give you another example of a reaction, what about hydrogenating benzene? We know you can hydrogenate alkenes and you get an alkane out of it. And the answer is you can hydrogenate benzene, but it's much more difficult than it is to hydrogenate alkenes. Platinum and palladium are not reactive enough. You have to use rhodium, RH, there in the D block somewhere. Might be under cobalt, or it might be under iron. Well, double check your periodic table. You'll find it in the D block. But you need to use an excess of hydrogen, of course, meaning at least 3 mole equivalents. And not only do you need a much more reactive metal, you also need to crank up the temperature and pressure to ridiculous heights. And then you can get cyclohexane. So that can be done. It's just much more difficult than for an alkene and requires much harsher conditions. I talk about this in the class notes mainly because it's in your book, and I just wanted to make sure that you guys understood it when you read about it. So the enthalpy of this reaction is minus 206 kilojoules per mole. It's exothermic. Of course, I don't care if you memorize that number. The thing is that if we estimated that enthalpy of reaction by considering benzene as though it were just a normal cyclic triene, the number we'd get would be minus 356 kilojoules per mole. That's off by 150 kilojoules per mole of what we actually see. And that shows us that benzene is more stable to the tune of 150 kilojoules per mole than we would otherwise have guessed if this were just an ordinary cyclic triene with localized double bonds. So this is what we mean when we say that benzene is an aromatic compound. It's got something going on in addition just to having those pi electrons, and in addition, even just to being resonance stabilized. There's something additional going on that's special about benzene and related compounds. And today we're going to start to get into that. All that really is evidence of is that this molecule is much more stable by about 150 kilojoules per mole, which is kind of a lot, by the way. If you're more of a joules person, we divide that by 4.184. Oh, what shall we call that? 30-something kilocalories per mole, something like that. I'm more of a joules man myself from my years of teaching Gen Chem. But that's just further evidence that benzene is special, that this reaction is less exothermic than we would otherwise have expected, had predicted, if benzene were just a cyclic triene. So the question is, what's the real nature of benzene and other molecules that are like it? For there are other molecules like that. And that's what we're going to start to get into today. We won't get to plumb the entire depth, so to speak, of how can you know if you're given a compound you've never seen before, whether it's aromatic or not. That's going to be our main topic, I would say, on Wednesday. But I do want to say a few things about naming aromatic compounds. First of all, it does say in your class notes, table 15.1 has several common aromatic compounds that I think you should commit to memory, their structures and their names. Yes, your exams will be open book, but you're going to save yourself a lot of trouble if you don't have to look those up every single time. Since these are very common molecules, so it's important to know their structures and their common names. Things like benzaldehyde, benzoic acid, right? Styrene is vinyl benzene. Toluene is methylbenzene. Acetophenone, phenylmethylketone. We're going to run into these things all the time. And so you're going to be at a disadvantage if those names don't immediately call up structures in your head. So it's useful to learn all of those structures and names. We'll use them repeatedly for the rest of the term. So that's fine. I also want to talk about naming multiply substituted aromatic compounds. I also want to remind you to review that annoying term benzilic, which does not mean what it sounds like it means. Benzilic does not mean aromatic. It means next to an aromatic carbon. So for instance, in toluene, which is methylbenzene, that methyl carbon is benzilic, not aromatic. The 6 carbons in the ring are aromatic. So it's an annoying term. It's very frustrating because it's confusing. But unfortunately, we're stuck with it. None of us was around when they came up with that term, and so no one was there to object. So just remember, if you see that word benzilic, it doesn't mean referring to an aromatic carbon or hydrogen attached to an aromatic carbon. It means next door to an aromatic carbon. So I also want to go over ortho, meta, and para. They're basically the 3 different types of di-substitution patterns of benzene. And I think if you look at it, yeah, everyone please register your attendance on REEF. I'm not sure if we'll do, I have a REEF session ready. If there is an ethyl group with the second carbon also be benzilic? Good question. Answer is no. The second carbon is not benzilic because it's 2 away from a benzene ring. Is there a term for that? Yes, homobenzilic. Do you really need to know that? Probably not. I can count on one hand the number of times I've needed that word over my career. But the one-word answer to your question is no. It's only the one right next to a benzene ring or a similar aromatic ring. So I think you'll agree these are the 3 types of substitution patterns that are possible on a benzene ring. And they go by a couple different names. You could call that 1,2 substitution or ortho. And sometimes they just abbreviate ortho to O. And we'll name a few of these compounds too. This one is 1,3 substitution or meta. You've probably already seen these terms. I bet you've run into them in lab. And there's finally 1,4 substitution, which we call para. Or you'll simply often see P. And what this means is that there is very often more than one correct name for an aromatic compound. So the way you use it is, for instance, oh, I don't know. Whoops, that wasn't what I intended. For no other reason than just to be bratty, I'm just going to turn the ring, just so you don't figure that the 2 groups have to be both on the right side of the molecule. But this one is 2 correct names. You could call that guy ortho-dibromobenzene or O-dibromobenzene. Or you could also call it 1,2-dibromobenzene. Both are perfectly acceptable. They are equally correct. There's no preference whatsoever for one over the other. What about a typical meta-disubstituted compound? Oh, what if we did this? What do you feel like putting over here? Methoxy. This one you could call meta-methoxy benzaldehyde. So you see why it's useful to know these trivial names. Or you could also call it 3-methoxy benzaldehyde. With the assumption that the carbon that bears the aldehyde group, since that's the one that the compound is going to be named after, or named for, is going to be carbon 1. So again, I can't say either of those names is any better than the other. They're equally acceptable. Let's see, I want to do, well, I could do a para one also. You can manage that. Why was it not 1,3-methoxy? Because the 1 is assumed, right? Because the carbon 1 bears the aldehyde group that we're naming the compound after. So benzaldehyde is also in that table on page 453 of compounds whose names you'll need to know. So since without the methoxy is just benzaldehyde, it's assumed that carbon 1 bears the aldehyde group. I'll do a para case also so that you can see. Oh, why don't I put, now that this compound probably is a trivial name also. Yeah, you can also call it meta-anisaldehyde, but we don't need to go that far as to learning all of those. That's not in the table anyway. How about, just because we feel like it, we put a tert-butyl group over here. 1 bird foot. So this one also you could call P tert-butyl aniline, since aniline is aminobenzene. And again, or again, you could call it 4-tert-butyl aniline. Because again, the carbon attached to the NH2 group is assumed to be carbon 1, since that's the one we're using to name the compound. So once again, I refuse to say that either of those names is any better than the other. They are equally acceptable, equally correct. What happens if you've got a tri-substituted or tetra-substituted compound? Then you can't use orthometa and para, right? Because there's multiple substitutions. So what I would try to do first, I mean, assuming that there's some group on the aromatic ring that takes precedence, like the aldehyde group or the carboxylic acid group or something like that. Otherwise, I think you'll agree a name like 1,2,3-trichlorobenzene is perfectly understandable. But short of that, oh, let's go crazy. Oops. So with something like this, again, this is going to be named as a benzoic acid. So the carbon that has the carboxylic acid group on it will be carbon 1. And we would number the carbons like this. Of course, 5 and 6 are there too. They just have hydrogens on it, so we don't worry about it. Well, I think we would be forced to call that 2-chloro-4-methyl benzoic acid. I think that's the best name. But I don't see a way to do that with orthometa para, because you've got a tri-substituted system. There we just have to number everything. But always you'll find that there's a functional group that takes priority and shows up in the name. And the way you know that is from the table on page 453. That's part of the reason why you need to know those names. It's going to make things much easier to name all these. But I mostly wanted to get you clued into orthometapara before we went on. Good. I think that's all I really needed to say about that. Questions so far? Oh, I should just also mention, so section 7 of this chapter is on spectroscopy of aromatic compounds. Well, we haven't done all the kinds of spectroscopy yet. Like, we haven't done NMR. So obviously you're not going to know about that until we do NMR. But there's going to be some types of spectroscopy we have covered, like IR. So of course, until we actually cover NMR spectroscopy, we'll learn about how it is that aromatic compounds, for instance, behave once we cover those types of spectroscopy. So I think that stands to reason, but I just want to be sure on that. Other than that, we've covered all of this. Good. So that leaves us about 20 minutes, which I think will be plenty of time to cover, to begin to consider how it is that we can tell whether a given compound is aromatic or not. Okay, so basically, a researcher named Huckel figured that out mostly by studying a wide array of compounds. And although, like I said, there's no way you can sort of look at a structure of a molecule and say the aromaticity of that compound is 5, like you can do with pH and pKa, still what we found in general is that there's 4 rules which we can tell by looking at the structure of a molecule, that as long as a compound obeys all 4 of those rules, and it has to be all 4 of them, but if it does obey all 4 of those rules, then we can conclude the compound is aromatic, meaning that it's something like benzene in how it behaves. And I've put these 4 Huckel rules into your class notes. Let's see if we can go over them now. Again, I'm used to teaching with chalk on a chalkboard, so I would be writing this on the board normally, but it's already in your class notes. So, but I do want to mention, if even one of these rules is not followed, game over. The molecule is not aromatic. So first of all, the compound must be planar. And we're going to have to go into that. You know, it begs the very obvious and reasonable question: how do you know if it's planar or not? And we'll see some interesting examples today. But I just thought I'd tell you up front, if all 3 other Huckel rules are followed and nothing prevents the molecule from being planar, then it is planar. What are some examples of things that prevent it from being planar? We'll get there. Secondly, the compound must be cyclic. That's clear. I think you can tell if something's cyclic or not. Number 3, all atoms in the ring must be sp2 hybridized. I'm not talking about atoms attached to ring atoms. I'm talking about the ones that are in the ring itself. And that's what we're going to spend most of Wednesday on, is how to know whether something's sp2 hybridized or not. But one thing that we can already be aware of, if there's, unless there's something preventing it from adopting sp2 hybridization, like having 4 sigma bonds, that would do it, right? Because an atom can't be sp2 hybridized if it has 4 sigma bonds attached to it. In that case, game over. But unless there's something preventing the atom from going to sp2 hybridization, it should be able to do so. And that's not just for carbons, by the way. Heteroatoms can certainly also be sp2 or sp3 hybridized. And last but not least, this is in no particular order. I would certainly never say to you, what is rule number 2? But I think you do need to know all 4 of those rules, at least in some sense, so that you can apply them. Did I answer? Oh yeah, I did answer this question about benzaldehyde. Good. The next has to do with counting pi electrons, which is also something we're largely going to have to cover next time. We'll begin today, but that's going to be an issue when we start getting into heterocycles, meaning cyclic compounds in which the ring atoms are something, it includes atoms in the ring other than carbon, so nitrogen or oxygen or all of these. We then come to the issue of non-bonding lone pair electrons. Are those pi electrons or not? And how can I know that? That's going to be a big topic again of next time. So, but the number of pi electrons has to fall into this series. It is to be 2 or 6 or 10 or 14, etc. And I think you can see each of these numbers is separated by 4. So you just add 4 to the previous number to get the next number. We already know, of course, that if there's a carbon-carbon double bond, that's going to contain 2 pi electrons. And in fact, if there's a double bond between any 2 atoms, doesn't have to just be carbon atoms, that's going to be 2 pi electrons. So we're going to start learning how to count pi electrons today. We're going to have to leave a big chunk of that until Wednesday, so don't worry. Now, the way this is usually described is some kind of rule involving 4n plus 2. And that's fine, but I've learned from experience over the past decade plus that simply stating that is not enough in terms of making that clear to students. Because the question immediately arises, well, what's n? You know, how can I figure out what n is by looking at the molecule? This is still a useful formula because I think you'll agree, as long as n is a non-negative integer, so it's as long as n is 0, 1, 2, 3, etc. Well, when you plug those non-negative integers respectively into that formula, you get 2, right? 4n plus 2, if n is 0, you get 2. If n is 1, you get 6. If n is 2, you get 10, and so forth. And that's all fine. But I want to be very clear, there is no way you can look at the structure and figure out what n is. So please, please don't try that. You'll be wasting your time. Or another way of saying the same thing is n has no physical significance. So if you're looking at structures and looking for your n and wondering if you're missing something, you're not missing anything. Okay, just don't even let that worry you. N has no physical significance. So that's why I prefer to tell students what you see here in your class notes, that the total number of pi electrons in the molecule must be exactly 2 or 6 or 10 or 14, etc. Has to fall into that pattern. Anything else, game over, not aromatic. So let's start, and maybe for the next 13 minutes or so, let's look at the so-called annulenes. So cyclobutadiene is also sometimes called 4-annuline, but no one really uses that name ever. Let's see how this works. Rule 1, compound must be planar. Well, I don't see how it could be otherwise. Right? If all 4 of those atoms are sp2 hybridized, which let's do all the others. Is it cyclic? Obviously, yes, it's cyclic. 3. Whoops. 3. Are all of those atoms sp2 hybridized? Yes, they have to be. They're all involved in a double bond. If it's fully conjugated, it's planar. Well, not necessarily. That's just it. But if there's only 4 atoms, it really is no choice. There's no way for it to pucker out of shape. And last but not least, the number of pi electrons is 4. So no, it violates that rule. So game over. Cyclobutadiene is not aromatic. And that's really what we use these 4 so-called Huckel rules for. Even though all the other 3 are true, or let's say we're still practicing and we're not sure if everything's sp2 hybridized. We're not sure if it's planar or not. Once we get to this, we can be absolutely certain there's only 4 pi electrons, right? 2, 4, 2 in each pi bond. So that ends it. We don't even need to consider the rest. Do you mind if I come to office hours and ask about pi electrons? Because I have no idea what they are. Well, we're going to learn as we go. I did give you one rule here that says that each carbon-carbon, I mean, you can still do that, but we'll have a lot more to say about that, including on Wednesday. Wednesday, that's going to be one of our main topics, how you can know whether where pi electrons are and what they are. But I did give you this rule here in the class notes. If you see a double bond, even not even just between carbons, but if you see a double bond, that's 2 pi electrons. The way you know that is a double bond consists of a pi bond and a single bond. Sorry, a pi bond and a sigma bond. So the sigma bond obviously contains 2 sigma electrons, the pi bond 2 pi electrons. So that much is clear. And that's all we'll really need for today. So yes, any of you is welcome to come to office hours, but I hope to clarify that, or at least set you guys on the path to clarifying that next time. Good, so much for 4-aniline or cyclobutadiene. It's not aromatic. Benzene would be 6-aniline, but no one ever calls it that. They just call it benzene. What about the 4 rules here? Is it planar? Well, yes. It kind of has to be. If you try to make a model, you'll notice it has to be. Do we need to call it anti-aromatic? We'll probably have something more to say about anti-aromaticity. Now, first of all, you're talking about cyclobutadiene. Yes, and we'll define anti-aromaticity and show when you need to say that something's anti-aromatic next time. Because, but I can give you a little bit now. We call something anti-aromatic in general if it's like cyclobutadiene. So, so in other words, it follows the first 3 Hückel rules, but not the 4th. So that should at least get you started. It's anti-aromatic if it follows the first 3 Hückel rules, but not the 4th. But like I said, we're just getting started. And you know, it's something that I can't show you all of it all at once. We got to go step by step by step here. So we're just going to deal with the first, you know, 5 or 6 anilines. So what do we do? Is it planar? Is it? Yes, it's cyclic, obviously. Are all of those sp2 hybridized? Yes. So that's one thing I should say. If you need to review hybridization, please do so. And we'll cover more of that the next time as well. How many pi electrons? 6 pi electrons. So yes, it does obey that rule. Right, 2, 4, 6, 1 for each of the pi bonds. So benzene is aromatic, which we already know. What about cyclooctatetraene, which is a thing? Well, let's see. Is it planar? I don't know. Maybe, maybe not. Let's go on. Maybe it won't matter. Is it cyclic? Yes. Are they all sp2 hybridized? Well, yes, they're all involved in a pi bond. What about number 4? Well, there's 8 pi electrons, so no. So we don't even care whether it's planar or not. I'll just tell you the molecule happens to be not planar. But even if it were, so here's an example of something you don't even need to know if it's planar or not. You can tell that's not going to be aromatic. And I actually had made a molecule of 10-aniline here. I wonder if I think quickly if I can turn this into a cyclooctatetraene molecule. Let me try, since I think that will be helpful. But yes. If you make a model, you will be able to see that this molecule is in fact not planar. Did I do it? Yes, there you go. Well, wait a minute. Yeah, there you go. So it's kind of tub-shaped. So you say, well, how can we have known that without making a model? Maybe you couldn't have. Now you know. But like I said, even if it were planar, this would not be aromatic. In fact, part of the reason that cyclooctatetraene buckles up into this tub shape is because if it were planar, it would be anti-aromatic, like Natalie asked about earlier. Again, we'll say more about that next time. Now I hope to turn this back into 10-aniline. We'll see if I can manage that. So, so much for that one. Let's look at the next several of these. Basically what we'll finish the class with today. Oops, I screwed that one up, didn't I? So the next one, again, very helpful oftentimes to make these models. There we go. Just need to put my hydrogen back on. Good. So let's look at the next one. Next one is commonly called 10-aniline. And I can draw it in about 3 mouse clicks. So here we go again. Let's see how the rules apply. Is it planar? I don't know. Let's come back to it. Is it cyclic? Obviously. Are all of those atoms sp2 hybridized? Well, yes, they have to be. They're all involved in a double bond. There's 10 pi electrons, so yes, it follows the fourth rule as well. So now, unfortunately, we need to go back and figure out whether it's planar or not. And again, I think it's easiest to tell if you make a model, which I've done here. And once you make a model, I think you'll be able to convince yourself very easily there's no way this can be planar. These hydrogens are like right in these carbon-hydrogen bonds in the middle for these two carbons in the middle of the ring fall right on top of each other. There's no way this molecule can be planar. So just because you need to make a model to be able to know whether it's planar or not, that's no issue. You're gaining insight. Can you use models in the exam? Well, no, and I think it would only take up time if you did. So in general, no, we don't allow models. But even now you're gaining insight from this particular example as to how you can know whether it's planar or not. And I think you'll agree. What have I done? Crap, I screwed that up again. I'm sorry. I thought I had that worked out. It's kind of similar to what we just saw. There we go. Now I've got it. Shouldn't look like a 5 and a 7. It should look like 2 6-membered rings. So there you go. Those fall right on top of one another. And I think even without making a model, if you just look at those two positions over here, this carbon and that carbon. Let me also make it a little bigger, maybe. This carbon and that carbon. It's right there that the problem is. Well, you can know that there's hydrogens on those two carbons. You can see there's still one bond missing. How can they not fall right on top of one another? So even without a model kit, I think you can tell. But with a model kit, it's very, very clear. So I think between your model kits and the OWL questions, you'll be able to get a pretty good idea of if there's a problem like that that's preventing the molecule from being planar. So it doesn't follow rule 1, game over. 10-aniline would be aromatic if only it could be planar, but there's no way it could be. What are some ways around that problem? Well, that's one. Just connect those two. and then the hydrogens are gone. You're probably familiar with that molecule. It's called naphthalene. It's one of the components of mothballs. There's another way to do it too. Another way around the problem, you just need to replace those, oh brother. I'm not seeing the exact bicyclic system that I would need. Oh well, basically if you connected those two carbons with a 1 carbon or 2 carbon bridge, 1 or 2 CH2s, that would also solve the problem. It's the hydrogens that are the problem. So I think you can see that this pattern continues. I don't even know if I have a 12-membered ring. I probably do. Cycloalkanes. Oh, look at this. You're going to be so jealous. That's a 12-membered ring. So we can put in our 1, 2, 3, 4, 5, 6 pi bonds for a total of 12 pi electrons. And I think you'll see already it's rule 4 that's the issue. Right? It doesn't follow rule 4. There's the wrong number of pi electrons. So 12 aniline is no good. What about the next one? And I would be hard-pressed to draw these by hand. Well, actually, some of these are not so hard. So here's your 14-membered ring. That would then have 14 pi electrons, 2, 4, 6, 8, 10, whoops, 12, 14. And so that's okay. That compound is aromatic. And I think you can tell, again, just by examining the structure, now there's plenty of room for these hydrogens that stick in the middle. There's plenty enough room for these guys. Unlike with 10 aniline. They're not all falling on top of each other. And the pattern continues. 16 aniline is the wrong number of pi electrons, so we don't even care if it's planar or not. Game over. 16 aniline is not aromatic. 18 aniline would be. And maybe it's already 11:32, but maybe for my last trick, I bet they have. Do they have an 18-membered ring for me? Yes, they do. It looks kind of cool, and I can do it in just one mouse click. So how do you like that? So now we get 18 pi electrons, 2, 4, 6, I know, 8. These are actually not as hard to draw as you might think, because they've got a nice regular shape. The final boss fight. Well, you can beat this boss. But you see, they make nice shapes. The 12-membered ring is a nice shape. The 14-membered ring, a nice shape. And the 18-membered ring, also a nice shape. Yeah, you see? So that one's going to be aromatic also. Both of those are aromatic. Loads and loads of room for those internal hydrogens. And I'm out of time. Actually, I'm a little over time, so sorry about that. But we'll pick up here on Wednesday. That's when we'll mainly cover these ideas of, we've already covered to some degree how to know whether something's planar, but we'll really get into that sp2 hybridization thing. And again, I'm not going to be able to do absolutely everything, but I'll at least hopefully get you started on being able to tell whether everything's sp2 hybridized or not. So have a good day. We'll see you on Wednesday. And you can enjoy the cats who are, oh, Barnaby woke up for a moment, but I'm sure he'll be back to sleep in 5 seconds.
Thank you.
Yep.